ഇത് ആവശ്യം വരില്ല. അവർക്ക് ഓൺലൈനായിട്ട് ഷെയർ ചെയ്യാൻ പറയാനുള്ളൂ, അതിന്റെ ആവശ്യം വരില്ല. ഞാനില്ലാതെ ഓഫ്ലൈനായിട്ട് വന്നാലും അഡ്മിറ്റ് ചെയ്തിട്ടല്ലേ തുടങ്ങൂല്ലേ? എല്ലാരും അഡ്മിറ്റ് ചെയ്തിട്ടുണ്ട്.
അൺമ്യൂട്ട്. ഓക്കെ ഓക്കെ, അൺമ്യൂട്ട് ചെയ്തോളൂ. നിങ്ങളാണോ അൺമ്യൂട്ട് ചെയ്യണത്? ഓക്കെ ആണ്. ഓക്കെ ഓക്കെ, താങ്ക് യു. ഓക്കെ 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 ഓക്കെ, താങ്ക് യു.
Good morning. Today we are going to start the oral online presentation session of STAM International Conference 2023 conducted by Marthanasius College, Kodamangalam. This is the second day of the conference. Our evaluators for the session is Dr. Sheena Xavier, St. Xavier's College, Alua, and Professor Dr. Malini K.A., Vimala College, Thrissur. We welcome you both for the session.
Thank you.
So our first presenter is Pooja Nayak, ID number 079. She is presenting on the topic polypyrrole or nickel molybdate composite for absorptive removal of toxic pollutants from wastewater.
Good morning, ma'am. Am I supposed to share my screen?
Pooja Naik, you can start your presentation now. I'll just read the instructions for the oral presentation. The presentation time is 8 minutes. Question and answers 2 minutes. Thank you.
Thank you. I'm not able to share my screen. It says the host has disabled screen sharing.
Can you please send your PPT to the mail?
I have already sent it yesterday.
Okay, then we'll share it.
Okay. Good morning, everyone. My name is Pooja Nayak. I am student of Christ University. Today, I'm going to be talking about adsorption of organic pollutants from aqueous solutions using polypyrrole nickel molybdate composite. As we know that water is the most essential resource for life on Earth, and the levels of water pollution is increasing day by day. One of the most important reasons for the water pollution is the effluents which are released by the industries, which includes acid, nitrates, phosphate, dyes, etc. So they alter the properties of the water and cause toxicity, mutagenicity, etc. There are several methods for the removal of these effluents, which includes physical, chemical, and biological methods. And out of this, adsorption was found to be the most effective method since it requires a very short period of time, does not produce harmful byproducts, and it is a very simple process. Can you please change to the next slide? There are various common adsorbents like activated carbon nanotubes, bioadsorbents, nanoparticles, etc. that are used for the adsorption process. Next slide, please. So for our study, we used polypyrrole and nickel molybdate. Polypyrrole was obtained from oxidative polymerization of pyrrole, and nickel molybdate was obtained from nickel nitrate and ammonium molybdate. So through studies, it was found that pure polypyrrole has a lower adsorption efficiency when compared to its complexes with metals. Hence, it was combined with nickel molybdate using in situ chemical oxidation polymerization. Next slide, please. Yeah. So nickel molybdate was synthesized from nickel nitrate and ammonium molybdate, and this was added to the polymerization mixture of polypyrrole, which include HCl, pyrrole, polyethylene glycol, and dropwise addition of ammonium persulfate to form the polypyrrole nickel molybdate composite. The application studies were done for the adsorption of methylene blue dye along with the catalyst polypyrrole nickel molybdate. So different amount of the catalyst, concentration of dye, temperature, pH, etc. were used to analyze its effect on the adsorption efficiency of the dye. And the adsorption efficiency was analyzed using UV visible spectrophotometer. Next slide, please. So various characterization techniques were performed. First one is the XRD analysis, which shows that the polypyrrole nickel molybdate composite has peaks for both polypyrrole and nickel molybdate, which are indicated in the table. Next slide. Similarly, for FTIR analysis, the bands for both polypyrrole and nickel molybdate indicating a specific functional group was present in the composite. The BET analysis showed that the surface area was 201.41, indicating a large surface area, which helps in better adsorption of cationic dyes. Similarly, pore volume was 0.22 cc per gram. Next slide, please. Next slide, please. The DLS and zeta potential were analyzed. So DLS was used to study the particle size. So pure polypyrrole had a particle size of 363, and the polypyrrole nickel molybdate composite had a particle size which was higher, and it was increased from 363 to 458. And similarly, the zeta potential was analyzed to study the surface charges, and it was more negative from -22.5 to -27.5. More negative zeta potential helps in better adsorption of cationic dyes. Next slide, please. The SEM and TEM images were analyzed. So the first image gives the SEM image of the polypyrrole, which shows spherical polypyrrole molecules. And the second image shows both spherical polypyrrole nickel molybdate, polypyrrole molecules along with rod-shaped nickel molybdate molecules. And image C and D give a better view of the internal structure. Image E indicates the SAED pattern, which indicates that the material is polycrystalline. Next slide, please. Yeah. So the XPS analysis shows that nickel is present in 2p form, molybdenum is present in 3D form, and nitrogen, carbon, and oxygen are present in 1s form. So that gives details about the various chemical constituents present in the composite. Next slide, please. So the given graph indicates that the absorption of methylene blue dye increases with the increase in time, and there is a decrease in the concentration of the methylene blue dye. So absorption is higher as the time increases. Next slide, please. So various applications were done, and first one, different types of dyes were used. So the absorption efficiency was found to be highest for methylene blue dye, and that is why it was used for further studies. As the amount of catalyst increased, there was an increase in the absorption. This was due to availability of more number of active binding sites. Similarly, as the concentration of dye increased, the absorption increased due to more interaction between the dye and the adsorbent. And as pH increased, the adsorption increased and reached a point of saturation. So at lower pH, the H plus ion concentration is high. That disrupts the bond between the dye and the catalyst. That's why adsorption was better at a higher pH. As temperature increases, the adsorption decreases. This is due to the increase in the kinetic energy of the molecules. So that leads to desorption process. Next slide, please. So adsorption isotherm and kinetic studies were done. So kinetic studies showed that the polypyrrole nickel molybdate composite followed pseudo second order kinetics, and hence it indicates that chemisorption takes place for the adsorption process. Adsorption isotherm also were studied, and that indicated that it followed Freundlich isotherm. Next slide, please. Freundlich isotherm, which indicates that the adsorption takes place in multi-layers on heterogeneous sites. Next slide, please. In conclusion, it can be said that the composite was easily synthesized from its precursor by in situ chemical oxidation polymerization. The various characterization techniques confirm the formation of the prepared composite. Adsorption activity increases with the increase in the concentration of the dye, amount of the catalyst, and pH. And adsorption activity was higher at lower temperatures. And Freundlich adsorption isotherm was followed by the composite, and pseudo second order kinetic model was followed for the adsorption process. Thank you.
So now it's time for the discussion.
Hello, Pooja. Good morning.
Good morning, ma'am.
That was a nice presentation, and I have few doubts, or rather clarification required.
Yes, ma'am.
You have prepared a composite of polypyrrole and nickel molybdenate, right?
Yes, ma'am.
And is it a heterogeneous structure, or they are your sample, final sample? You said your XRD contains both.
Yes, ma'am.
Polypyrrole and molybdenum structure components, as well as FDIR also confirms both, right?
Yes, ma'am.
So that means it is it's like a heterogeneous.
Yes, ma'am. Yes. Yes.
And may I know what is the motivation behind using this polypyrrole nickel molybdenate composite?
Yeah. So pristine polypyrrole, the pure polypyrrole, usually helps in adsorption, but it was found that the adsorption was not very high. Similarly, only nickel molybdate also was used in adsorption, but that also didn't have very high adsorption efficiency. So when these two were combined together, the adsorption efficiency reached to almost 98%. So that is why these two components were combined together.
When you come to the application,
yes, ma'am.
Say if you are using it for dye degradation applications, will there be any other effects of molybdenate, side effects of molybdenate in the system?
As of now, through our studies, we have not found any side effects.
Have you done any such studies? Or
on real water sample, we have to do the further studies. As of now, we have just done on the laboratory sample. So that is the scope of our further research, where we'll be talking about, where we'll be doing research on real water samples collected from various lakes which are highly polluted.
Do you expect methylene blue to be present in the lake water, or?
Yes, so methylene blue is a very common dye which is released into the water, and actually there are various other types also of dyes also. So our composite can helps in it helps in absorption of all those kinds of dyes, but it shows higher levels of absorptions for methylene blue.
Okay, fine.
Yes,
Shila ma'am.
Okay, Pooja.
Yes, ma'am.
I would like to clarify some points.
Yes, ma'am.
What are some of the examples of pollutants that can be removed using this polypyrrole composite?
So
In-
for as of now, we
In
have
industry
conducted.
or environmental?
As of now, we have worked on specifically dyes, but
Okay.
further we can think of nitrates, phosphates, etc.
Okay, what another question is, what is the advantage of this composite over other ones?
Yes, so when we take other composites, for example, activated carbon, so those do not have very high absorption efficiency, and also they can be expensive to synthesize and the regeneration capacity is less. But our composite, it can be synthesized using very minimal precursors, and it requires a very short period of time for synthesis, and also gives high absorption when compared to the activated carbon.
Okay, okay, Pooja.
Yes, ma'am.
Thank you.
Thank you, ma'am.
Thank you, Pooja.
Thank you,
So
ma'am.
our next contestant, our next presenter is Dinu Alexander, ID number 069. He is presenting on spectroscopic analysis of calcium tungstate and EU-doped calcium tungstate phosphor material. Dinu, please.
Okay. Actually, it is seen that host disabled participant screen sharing. Can you change it?
Okay, can you send the presentation to our mail ID?
Already I have sent it.
Okay, they will check.
Can you hear me?
Yes, ma'am.
Okay, okay.
Is visible now. Ma'am, can I present now?
Yeah.
Yeah, sure.
Okay,
Yes.
good morning to all. My work is spectroscopic characterization of calcium tungstate and European doped calcium tungstate phosphor. Can you move to next slide? Next slide, please. Okay. We all know that phosphor find applications in lighting and display field, and some of the basic requirements needed for a phosphor material include intense emission, good RGB color purity, high thermal stability of luminescence, and low protection cost, etc. And coming to nanophosphors, next slide, please. Coming to nanophosphors, they are nanostructured materials and they emit light under suitable excitation. Usually they appear in powder or film, etc. And some of the advantages of nanophosphors include higher packing density and lesser non-radiative losses, etc. Next slide, please. And the basic composition of an inorganic phosphor means it consists of a crystalline host and activate ions. That is, crystalline host plus activate ions gives the phosphor material. And here, both the host material and activate ions influences the luminescence properties of the phosphor material. And some of the examples of host materials includes oxides, molybdates, phosphates, tungstate, etc. And examples of activate ions are rare earth ions, bismuth, chromium, etc. Among these, the rare earth ions are of special importance due to its special optical properties. Next slide, please. Among the rare earth ions, it has special luminescence properties since it has sharp emission, and also it is well shielded by the outer, the 4 of electronic levels of rare earth ions are well shielded by the outer 5s2 and 5p6 electrons. Therefore, it has sharp emission, and also the rare earth ions have emissions in the entire spectral range, that is from UV to near IR. For red emission, we can use europium samarium, and for green emission, we can use terbium. For yellow emission, we can use dysprosium. While in the present work, we have selected the host material as tungstate, and we have selected the europium as the activator ion for red emission. Next slide, please. The samples, that is the calcium tungstate and European doped calcium tungstate phosphor materials, were prepared by simple co-precipitation method. And this is the flowchart of the synthesis procedure here. 0.1 molar aqueous solutions of calcium nitrate and 0.1 molar aqueous solution of sodium tungstate is prepared, and the solutions were stirred well for 30 minutes and they were mixed, and the product obtained were washed with the deionized water and dried it for 70 degrees Celsius. And finally, the samples were calcined at 600 degrees Celsius for 3 hours in furnace, and the samples obtained were grinded for 30 minutes, and the samples obtained, that is the calcium tungstate and europium doped calcium tungstate, were further characterized by using various characterization techniques like XRD and photoluminescence studies. Next slide. Now we can see the X-ray powder diffraction analysis of the prepared samples. Here, the XRD of calcium tungstate and 5% EU doped calcium tungstate is given in the figure. All the peaks of the XRD matches well with the ICD of calcium tungstate, and the crystal system is found to be tetragonal. The particle size, that is crystallized size, calculated from the Bézier equation is found to be in the range 15 to 16 nanometer. These are the main conclusions of X-ray powder diffraction analysis. Next slide, please. Moving to photoluminescence studies, first we see the photoluminescence analysis of calcium tungstate phosphor. First figure is the excitation spectrum, and second figure is the emission spectrum. When we look into the excitation spectrum, it is recorded on monitoring the 420 nanometer emission of the tungstate group. Here we can see a broad excitation band. This broad excitation band is assigned to the charge transfer, metal charge transfer band of tungstate group. And also we have recorded the emission spectrum on exciting the sample at 256 nanometer. Here we can see a broad emission spectrum and it is centered around 420 nanometer. Here we have concluded the excitation and emission spectrum of calcium tungstate phosphor. Next slide, please. And coming to the photoluminescence studies of European doped calcium tungstate nanocrystal, we have recorded both the excitation spectrum and emission spectrum. This is the excitation spectrum of the sample. When we look into the excitation spectrum, we can see initially a broad band in the range 200 to 300 nanometer, and it is assigned to the charge transfer transition of tungstate group. After this broad excitation peak, we can see a series of sharp peaks, and all these sharp peaks are assigned to the various peaks of the europium ion, and all the assigned peaks are shown in the figure. Next slide, please. And This is the emission spectrum. We have recorded the emission spectrum under two different excitations. The first excitation, that is, and the first figure is the emission spectrum recorded under host excitation, that is at 256 nanometer. And the second figure is the emission spectrum of the European doped calcium tungsten nanophosphor recorded under the direct excitation of europium ion. Coming to the first figure, we can see that with the excitation of charge transfer band, we can see the emission peaks of europium, which clearly indicates the charge transfer transition, that is energy transfer have been occurred from tungstate group to europium ion, while under direct excitation of europium ion, we can see the characteristics emission peaks of europium ion only. Next slide, please. The above mentioned emission process can be distinguished from this figure, that is the energy transfer diagram. Here we can see the valence band of tungstate group, and this is the conduction band of tungstate group. Under host excitation, that is under 256 nanometer excitation, electrons from the valence band of WO group will get excited to the conduction band. From there, a part of energy is transferred to the europium ion. This europium ions will get de-excited to the 5d0 level. This 5d0 level is the metastable level of europium ion. From there, the ions will get de-excited to the lower 7 levels of europium ion. These are the ground levels of europium ion. From there, we got the emission peaks at 592 nanometer, 616 nanometer, and 652 nanometer. Thus, the prominent render emission is obtained at 616 nanometer, and this can be assigned to the 5d0 7 of 2 transitions of europium ion. While under direct excitation, that is under 350 nanometer, 394 nanometer excitation, the europium ions will get excited to its excited level. From there, it will get de-excited to the 5d0 level. From the 5d0 metastable level, we get the different distinguished characteristic emission peaks of europium ion in the case of direct excitation also. Next slide, please. Okay. Then this all we have discussed some of the spectroscopic analysis of europium doped calcium tungstate, and we all are familiar with the Jude-Ophel theoretical analysis. We all know that Jude-Ophel theoretic analysis is a technique used to describe the spectroscopic parameters of the host material. Usually, the Jude-Ophel theoretical analysis is carried out from the UV visible spectrum, while in the case of europium ion, we can find out it easily from the emission spectrum of europium ion. And in the from the emission spectrum, I have discussed earlier. By using that emission spectrum, I have calculated the spectroscopic parameters of this tungstate group by using the emission spectrum. For that, we have to find out the JO intensity parameters. The JO intensity parameters are denoted as omega 2, omega 4, omega 6. These JO intensity parameters are calculated using this equation. For that, we have used the emission peaks, that is the 5d0 7 of 2, 5d0 7 of 4, transitions of europium ion. These are electric dipole transitions, and we kept the magnetic dipole transition 5d0 7 of 1 as a reference line, and we have evaluated the J intensity parameters, and it is found to be in the range omega 2 greater, omega 4 greater, omega 6. Here we can see the high value of omega 2 is obtained, which indicates that europium ions are situating in the tungstate group, the tungstate host, in an asymmetric site. Next slide, please. And from the evaluated J intensity parameters, that is from the omega parameters, we can find out the different radiative parameters of europium activated calcium tungsten nanocrystal, and we have find out the peak wavelength, transition probability, branching ratio, effective bandwidth, and emission cross section. And we can see from this table the emission, all these parameters, all these radiative parameters are found to be higher for the 5d0 to 7 of 2 transition, and this is matches well with the experimental spectrum also. And we have compared the radiative parameters of this particular transition with the reported other europium doped materials, and from this table we can see that we have obtained almost comparable and high value of all the radiative parameters for this europium doped calcium tungstate with the other reported materials. These are the main conclusions of the theoretical analysis. Okay, next slide, please. And this is the CA diagram. CA diagram actually indicate the emission color of this material. We can see under host excitation, the emission color from the sample lies in the blue region, while for under 394 nanometer excitation, the emission color from the sample lies in the red region. Thus, we can use this phosphor for blue color purpose and for red color purpose under different excitation. Next slide, please. Thus, the major conclusions of the work are the calcium tungstate and European doped calcium tungstate nanocrystals were prepared by simple co-precipitation method, and the average crystalline size obtained was below 20 nanometer. The photoluminescence analysis carried out by recording the excitation emission spectrum of the pure and European doped samples. The geotheoretical analysis shows the high value of emission cross-section and branching ratio for 616 nanometer emission, and it suggests the utility of this material for various display and optical purposes. Thank you.
It's time for the
Okay,
discussion.
Dino. Okay, Dino, that's a good presentation.
Thank you, ma'am.
How can we use this analysis, spectroscopic analysis, to optimize this luminescence efficiency of these materials you have used?
I have carried out the spectroscopic analysis. First one is the luminescence spectrum. From the luminescence spectrum, we can see that the material is excitable under wide excitation can be used. Since the excitation spectrum clearly indicates that under 616 nanometer monitoring excitation, we can see a broad peak initially, and after that a series of sharp peaks were obtained. Thus we can use this material, or we can excite this material under various possible excitation. This is the first conclusion. And after that, we have carried out the spectroscopic quality of this host material by Judoffel theoretical analysis. From there, we can find out the high value of stimulated emission cross-section. Actually, the stimulation emission cross-section indicate the lasing power of a material. And for this particular material, it is high or it is comparable to other reported values. So it is a good material. We can conclude for red emission.
Okay. Can you give some potential applications of these materials?
Okay, it can be used in initially in LED or in white LED purpose. We can use this one since it gives red emission under 394 nanometer excitation. It is NUV excitable, and also it can be used in display purposes and other lighting applications. We can use red LEDs. We can construct using this material, and also we can use it in anti-counterfeiting application. Also, we can use this material since the material is MC only under in UV or UV, so it can be used in anti-counterfeiting purpose also.
Okay, thank you, Dino. Over to Malini.
Yeah, thank you, ma'am. That was a good presentation, and I have a few doubts or rather clarifications. Can you kindly go to your XRD slide?
Okay, so actually the host is...
Yeah, it's okay. It's okay. Okay, I just want to know whether there is any fingerprint of europium in your XRD.
Actually, the both the XRD pattern of calcium tungstate and the europium doped calcium tungstate are similar.
Yeah, so it exactly similar. There is no
presence of europium.
Yeah,
from XRD, we can confirm the presence of europium.
Okay, it is not possible.
Not possible, but it can be confirmed from the luminescence studies, ma'am.
And regarding the intensity axis of your spectrum, what is the power of that factor? It's very high, it seems.
Yes, it is very high, ma'am. It is of the order of, I think, 10⁵, seems like that. 1 into this.
So you'll be getting that much intense.
Yes, it is intense, ma'am. Since the rare earth ion are from initially, I have said that rare earth ions are sharp and intense emission. And then this is one of the property of the rare earth ion, that is europium ion.
But without europium top sample also sample without europium also shows intense lines, like.
But intense, but it is not sharp. It is broad. It seems to be broad for calcium tungstate. But for LED purpose and some other purpose, we need sharp emission.
Okay.
So for that purpose, we have doped the europium into this calcium tungstate. We need actually for a luminescent material, we need broad excitation and sharp emission.
Sharp.
This is okay.
And I would also like to know what are the other materials that can be, other than tungstates, what are the materials or common materials that are being used for these applications?
Okay, for lighting purpose or LED purpose, we need high temperature stability materials. For that, we can use tungstate. In addition to tungstate, we can use phosphate, molybdate, etc.
Okay,
Or
tungstates.
titanate. Or titanate.
So the advantage of tungstate is?
Tungstate is it is highly stable. Its temperature stability is very high compared to all other materials, and also it have broad excitation. And this is one of the other advantage of this material.
Okay, fine. Thank you.
Okay, thank you, ma'am.
ഇവരൊക്കെ ലിറ്ററേച്ചർ റിവ്യൂ ഒക്കെ പറയുന്നുണ്ടോ? ഇല്ല. ഒബ്ജക്റ്റീവ് പറയാം. കുറേ പണിയുണ്ട്.
Thank you, Dino.
Okay, thank you, ma'am. Okay.
Presenters, please note that the time for the presentation is 8 minutes and the question answer session is 2 minutes. I request all the presenters to stick on to the time. Our next presenter is Smita Bhaskaran, ID number 070, title Comparative Study of Structural Properties of Oleic Acid Coated Metal Nanoparticles by Co-Precipitation Method.
Please mute Nirosha. It seems.
Good morning, ma'am.
Good morning, but there is some disturbance. House, please mute Nirosha James. Who is Nirosha James?
Good morning, ma'am. May I start my presentation?
Yes, please. Yes.
Yes.
Good morning. Is it visible?
Yes, yes.
Yes.
I am Smita Bhaskaran, doing my research under the guidance of Dr. Veena Gopalan at Department of Physics, Vimala College, Thrissur. Here I am presenting my work on a topic, comparative study of structural properties of oleic acid coated metal nanoparticles, cobalt, nickel, and iron by co-precipitation method. Metal nanoparticles find many applications in optoelectronic devices as catalysts and as biosensors. Conventional methods for synthesis of metal nanoparticles are very difficult. So coating the metal nanoparticles is needed for preventing the nanoparticles from oxidation. And in the present work, cobalt, nickel, and iron metal nanoparticles are synthesized by co-precipitation method. Oleic acid is coated on the metal nanoparticles to prevent them from oxidation. Structural properties of coated and uncoated metal nanoparticles are studied using XRD and FTIR. And in the XRD, we observe the formation of graphitic structure on the nickel and iron metal nanoparticles. This is the experimental method to synthesize the metal nanoparticles. The precursors used for the synthesis are metal salts of corresponding metals, that is cobalt sulfide in case of cobalt metal nanoparticle, nickel nitrate in case of nickel metal nanoparticle, ferric chloride in case of iron metal nanoparticle, and sodium borohydride as the reducing agent. Sufficient amount of sodium borohydride is added to the metal salt solution with constant stirring. The solution is turned to black precipitate and it is dried in an oven to get pristine sample. And oleic acid is coated on these metal nanoparticles. For this, the black precipitate is washed several times and oleic acid is added drop by drop. And water is separated from this oleic acid coated sample. The sample is fully coated with the oleic acid, and water is separated from this oleic acid coated sample, and they are dried in an oven. The structural characterization were carried out by XRD analysis and also with the FTIR measurements. And these are the XRD pattern of uncoated metal nanoparticles and the coated metal, oleic acid coated metal nanoparticles. So the crystallite size estimated from the XRD pattern are listed in the table. And in the uncoated metal nanoparticles, it is seen that the XRD pattern shows the prominent peaks of metal oxide phases. And when they are coated with the oleic acid, the XRD pattern shows the prominent peaks of metal oxides, metal nanoparticles rather than the metal oxide peaks. And from the XRD, the presence of graphitic structure in oleic acid coated metal nanoparticles are found out. And nearly 2 theta at 20 degree, a broad prominent peak is present, which is reported to be the reflection from 002 plane of graphite. And the broadness may be due to the formation of sheet-like structures of graphite. The FTIR analysis of oleic acid coated metal nanoparticles are shown in these figures. And in this FTIR spectrum, the bands of metal oxides and also the oleic acid are present. The absorption bands at 580 centimeter inverse was assigned to cobalt oxide stretching vibration mode, and at a 674 centimeter inverse was that of the bridging vibration of cobalt oxygen bonds in CO3O4 phase of the sample in figure A. And in figure B, the presence of metal oxide nickel oxygen bond is evident from the peak at 668 centimeter inverse. And in figure C, the band at 587 centimeter inverse corresponds to the vibration of iron oxide bonds in the structure of Fe3O4. The peaks at 1438 centimeter inverse and 1518 centimeter inverse were attributed to the asymmetric and symmetric stretching vibrations of COO functional group, which confirms that the oleic acid is coated on the surface of the nanoparticles. Then magnetic properties of cobalt metallic particles are studied using VSM. The MH curves of cobalt pristine and oleic acid coated cobalt metal nanoparticles are shown in the figure. And from the MH curves, the magnetic parameters are calculated and it is listed. The saturation magnetization decreases as oleic acid is coated on the metal nanoparticle. And these are the magnetic properties of the cobalt pristine and oleic acid coated cobalt metal particles. And it is concluded that cobalt, nickel, and iron metal nanoparticles are synthesized by chemical co-precipitation method. The synthesized metal particles are coated with the oleic acid to prevent them from oxidation. XRD patterns of oleic acid coated metal nanoparticles show the presence of metal nanoparticles along with the metallic oxide phases. Cobalt oxide in case of cobalt, nickel oxide in case of nickel, and Fe3O4 in case of iron. The crystallite size estimated from the XRD data is found to be in the range 3 nanometer to 13 nanometer. Then it is found that the broad peak centered at 20 to 21 degree in the XRD is due to the graphitic structures typically obtained from 002 reflections of graphite. Thank you, ma'am.
Okay, Smita. Can you hear me?
Yeah, yes, miss.
Okay. That was a good presentation. I would like to clarify some points. Why do you choose this co-precipitation method for this samples?
The reduction method is very easy technique. This co-precipitation
Okay.
with
What is
reduction.
that? What I am asking, what is the advantage of using this method? There are other methods to prepare this nanoparticles. Okay.
Yeah. Co-precipitation method, it is using this method we get homogeneous nanoparticles, and it is very easy to synthesis this
but the
reaction.
XRD shows it is in the amorphous side, isn't it?
Yes, miss, that is metal oxide peaks are present in this. It is very difficult to synthesis this metal nanoparticles due to its instability. But
okay,
using this method, we can easily prepare metal nanoparticles. But some peaks are there. I mean, metal oxide peaks are there in the XRD pattern. But when
okay,
it is coated with oleic acid, the metal nanoparticles are somewhat protected from the oxidation.
Okay.
Miss.
Over to you, ma'am.
Yeah, thank you, ma'am and Smita, for
Yes,
the
please.
presentation. And I need some clarification, like in your slide size calculation, as Sheena ma'am has asked, I have the same doubt that your sample contains metal as well as metal oxides.
Yes.
Right?
Yeah.
And FTIR also shows presence of metal oxide.
Yes.
And is there any method to eliminate these metal oxides and isolate the metal nanoparticles from your sample? Have you read anything regarding that, or is there any method?
Actually, we are trying one more method in polystyrene nanocomposites. The metal oxide metals particles are embedded in polystyrene nanocomposites. That is the next method we will be using to protect these metal particles.
From oxidation.
So first we tried with the oleic acid coating, and then next we will do the next method. Okay. From the given from the results of this work. Then next we have to do the next method. Okay.
And my another doubt is in your XRD from your slide, you have calculated the slide size from your XRD.
Yes,
and what I have seen is that your cobalt sample alone, the coated sample has got lesser the slide size than that of uncoated. Why? Oleic acid coated sample has the slide size less than the pristine sample. Why is it so?
In the uncoated samples, the oxide peaks are dominating.
Okay.
Metal oxide peaks are dominating, and in oleic acid coated samples, the metal particles, the phase of the metal particles are dominating, and they are protected from the oxidation, and that gives only the size of the metal nanoparticles.
But it is the other way in the other two metal metal systems. Right.
In nickel, it is somewhat difficult to protect this nickel metal particles alone.
Okay, and one more point I would like to know is your pristine cobalt and oleic acid cobalt, when you compare it, your Hc value increases when you coat it, but your MS value decreases. That is, fissivity value increases and magnetization value decreases.
Yes, miss. That is decrease in saturation. It is due to the
Magnetic component. Okay.
non-magnetic phase of the organic oleic acid. But Hc value, it may be, we think that it may be due to the that cobalt has a high coercivity,
Okay.
and cobalt is protected from the oxidation while when it is coated with oleic acid, and we are getting more coercive values due to that cobalt phase.
Okay, fine. Okay. Thank you.
Okay, thank you, Miss.
Thank you, Smita Bhaskaran.
Thank you.
The next presenter is Aparna N, ID number 071. The title is Dark Catalytic Activity of Tin Sulfide Thin Film Deposited at Room Temperature.
Good morning. Am I audible?
Yes.
Hello.
Yes.
Yes.
Good morning, all. I'm Aparna N, Assistant Professor, St. Joseph's College, Devagiri. It is reported that about 70 to 20% of water pollution is caused by textile dyeing. Here I am presenting my work on the dark catalytic degradation of textile dyes using thin monosulfide thin films deposited at room temperature. Advanced oxidation processes are an important class of processes for the wastewater treatment. AOPs utilizes highly reactive species like hydroxyl radical produced in situ for the degradation of harmful organic pollutants into non-toxic or less toxic molecules. Dark catalysis is an AOP which can be carried out at the dark at ambient temperature and atmospheric pressure. As dark catalysis do not need any external energy or chemical reagent. It is more advantageous than other advanced oxidation processes. For this method, the catalyst was thin monosulfide thin film. It was prepared using a modified chemical method named as successive layer adsorption and reaction. In this method, the pre-cleaned substrate is alternatively dipped in cationic and anionic precursor solutions. The cationic precursor was stannous chloride dihydrate and anionic precursor was sodium sulfate. The expected reaction is SN2 plus S2 minus giving SNS. The most important factor is that we were able to deposit the thin film at the room temperature itself. It is a very simple, cost-effective method which gives high degree of substrate tolerance, good control over thickness, and only needs low operating temperature. It is very easy to vary the stoichiometry of the thin film in this method. We deposited the thin film by varying the cationic molarity from 0.03 molar to 0.05 molar, where anionic molarity was fixed as 0.03 molar. XRD results confirm the formation of polycrystalline SNS thin film with the orthorhombic crystal structure. There was only the sample prepared with the 0.03 molar cationic solution named as C.03 showed SNS2 peak. All other samples showed SNS peaks only. An increase in SN concentration with the increase in the cationic molarity was observed from the IDAX measurements, and the TGA analysis showed that all the samples are thermally stable. And an increase in the band gap with increase in the cationic molarity can be correlated to the increased thickness due to more amount of material deposited. For example, 0.03 exhibited an extraordinary behavior. It showed a greater band gap of 1.6. It may be due to the presence of SNS2 phase, which is reported to have a higher band gap than the SNS phase. And some images of some samples are shown. XPS result confirmed the formation of SNS. And due to the abundance of constituent elements, cost effectiveness, less toxicity, etc., SNS is suitable for any device fabrication. Its chemical stability, low aqueous solubility, layered structure, inert nature, etc., make it a good catalyst. Aqueous solution of methylene blue with the catalyst was maintained at the dark condition with continuous magnetic stirring. 3 ml of solutions were taken out from the reaction mixture in 15 minutes interval, and UV visible spectrum was recorded. A color decrease in the color with the reaction time is observed, and UV visible spectra absorption peak also decreased with time. A graph of logarithm of C0 by C. C0 is the initial concentration and C is the present concentration. Also, a graph of logarithm of C0 by C with reaction time is a straight line, which indicates that the reaction is following a pseudo first order kinetics. LCMS analysis data before and after of the methylene blue solution, before and after catalytic treatment is shown here. And this is the initial solution, and this is the LCMS graph of solution treated after after catalytic treatment. A decrease in the methylene blue peak and emergence of new peaks indicated that it's not an absorption but the degradation. And the decrease in the catalytic activity in the presence of OH radical scavenger confirmed the role of OH radicals in the degradation process. And to confirm it, we conducted OH radical indicator test using terephthalic acid also. And as it is a heterogeneous catalyst in the form of thin films, it's very easy to recover the catalyst after use from the solution. It is thermally and structurally stable after the use, and the catalyst was able to use without much loss in the degradation efficiency for 5 consecutive trials. And our catalyst was able to degrade both cationic and anionic dyes. We also tried the catalytic efficiency against a commercially available dye of the brand Chakra. It also gave good results. And it is a proposed dye degradation process. First step is the adsorption of dye molecule onto the surface of thin film catalyst. And the SNS is in the SN2 plus state originally, which loses 2 electrons and will become SN4 plus state. These electrons will migrate to the surface of the catalyst, where it will undergo a series of chemical reactions to produce hydroxyl radical. Hydroxyl radicals are highly reactive. It will react the methylene blue molecule, and it will degrade methylene blue molecule into non-toxic or less toxic product. That is the mechanism happening here. And an increase in the catalytic activity due to magnetic stirring is due to the increased contact between catalyst and the dye molecule due to stirring, and also due to the increased amount of dissolved oxygen in the solution due to stirring. We found that there is an optimum concentration of dye for the maximum dye degradation, and an increase in the catalytic activity was exhibited by the samples with more amount of tin. This is due to the increased absorption and the enhancement in the electron exchange. And our material is known as a class of material known as van der Waals epitaxis, where interlayer bonds are very strong and intralayer bonds are weak. So it offers high degree of substrate tolerance. We were able to deposit the thin film on a very flexible substrate also. It is also characterized, and the thin film on the flexible substrate also exhibited good dark catalytic activity. So let me conclude my presentation. The thin monosulfide thin films prepared using successive layer adsorption and reaction method is a highly efficient and stable catalyst for the degradation of textile dyes. The deposition is possible at room temperature and also on flexible substrate. An increase in the catalytic activity was observed with magnetic stirring and in the amount of tin concentration, and there is an optimum concentration of dye for best catalytic performance. Thank you. Hello. Hello.
Hello, Aparna. Can you hear me?
Yeah, ma'am. Okay.
That was okay. That was a good presentation. I would like to clarify some points. You have said that this film is coated on different substrates.
Yeah.
What are the different substrates you have used?
The main deposition was on the glass substrate. It was possible to deposit on glass. Then we tried an OHP sheet, commercially available OHP sheet, a flexible substrate. It is also a thermally sensitive substrate, and we were able to deposit the film on that also.
And how is this activity depends on the substrate? How this
I didn't compare like that, ma'am. I just studied both. The main studies were on the thin film deposited on the glass substrate, and I varied many parameters. I just deposited it on the flexible substrate and also studied that it is also showing dark catalytic activity. I didn't compare the substrate, importance of substrate here.
Okay. You have studied the SEM analysis of the sample, isn't it?
Of only 2 selected samples, ma'am.
Okay. Have you analyzed the effect of this morphology on the study?
No, ma'am.
Okay. Okay. That's all. Over to you, Malini.
Yeah, thank you, ma'am. And Aparna, I also have few doubts or rather clarifications. What could be the thickness of the films, approximate thickness of the films that you have used on glass substrate as well as?
Actually, for this we fabricated comparatively thicker films. It is in the order of 1 micrometer.
What about that on your OHP film?
It is having a comparatively lesser thickness, ma'am.
And what about the shelf life of these films, both on glass as well as flexible films?
Truly speaking, ma'am, after 3 to 4 months, it is degrading, changing color.
That means it is having some reaction with the atmosphere.
Yes.
And you were talking about using that dye solution or something like that. That advantage of this method you were telling about, you can reuse the dye solution. Clear about. Just elaborate.
Pardon, ma'am?
You were telling about you can reuse the dye solution.
Is this slide, ma'am?
No, in your, just go to your, I don't remember the slide number, just slides. Your, maybe by the end of your, yeah, just, in your conclusion. Easy recovery from dye solution after use means your catalyst can be, that's.
A catalyst can be easily recovered.
Okay,
if it is
okay,
a
I got confused. Yeah, I got
okay.
confused. Yeah, it's okay. And why there is no unit in your absorbance curve, y-axis unit? Your absorption spectrum doesn't show, doesn't have a unit in the y-axis.
Absorbance.
Your absorption spectrum.
Sorry, ma'am. Actually, it's just intensity, and we are just taking the relative intensity.
No. I was no. You have calculated the band gap, right? I was talking about that curve. This is okay. This you are getting the relative value. Here also you don't. You have not absorbance in arbitrary units. Okay, fine. Thank you.
Sorry, ma'am, I will correct it.
Yeah, it's okay. It's okay.
Ma'am, I have some doubt.
Yeah, please.
Hello.
Yeah, please.
Ma'am, what is the degradation efficiency of this film?
The film was able to degrade the dye 98% within 75 minutes.
Okay. Then how can determine the direct band gap material?
Yes, it's a direct. Actually, it have both reported that it also have already direct and indirect band gap material. And I found my material as direct band gap material. It is ranging from 1.48 to 1.88 in this deposition conditions.
Okay, thank you.
Okay, then thank you, Aparna.
Thank
Thank
you. The next presenter is Anu Philip, ID 072. Title: Comparative Study of Optical and Dielectric Properties of PVA and Silver Doped PVA.
Good morning. Am I audible?
Yes.
My slide is visible?
No, the slide is not visible.
Now it's visible?
Yes.
Yes.
Okay. With your permission, let me start my comparative study of optical and dielectric properties of PVA and silver doped PVA. Metal polymer nanocomposites have been identified in academy and industry as a promising candidate in modern science and technology. In contrast to the intrinsic metal oxide or noble metal multilayer, metal polymer nanocomposites are currently being of interest because of their distinctive qualities like outstanding multifunctionality, potential for large-scale manufacturing, a considerable weight reduction compared to metal, and ease of synthesis. Polymer nanocomposites demonstrate superior qualities to pure PVA because they do not require any modification to the processing of polymers. The combination of organic and inorganic material properties of the metal polymer nanocomposites exhibits make them appropriate innovative material to use in various applications like microelectronic devices, sensors, electromagnetic shielding, charge storage capacitor. This study investigates the effect of optical and dielectric properties of PVA with AG doping. The structural characterization of the study were done using XRD analysis, optical characterization performed by FTIR and UV visible spectroscopy. Dielectric measurements were done on both doped and undoped samples using impedance analyzer. In this study, I used the material, polymer material is PVA and the metal as silver. The method of deposition is a simple solution casting method. Why I choose PVA? Due to its superior properties like non-toxicity, low cost, good transparency, biocompatibility. Moreover, it has many applications in industry nowadays. This slide shows the XRD pattern of pure and silver doped PVA. So the red one is the silver doped PVA and black one is PVA. Both have shows the amorphous nature of the prepared samples. This is almost compatible, almost similar to the reported values of PVA. Coming to the optical analysis, the optical absorption spectra of pure PVA and AG doped samples are shown in figure. The characteristic peak of pure PVA is observed at 190 nanometer and 280 nanometer. There is no peak observed in the visible region. And in the case of silver doped PVA, there is an additional peak observed at 424 nanometer. This is the characteristic peak of silver nano. that is due to surface plasmon resonance. We also calculate the band gap of this PVA, pure PVA and silver doped PVA by Doppler. This slide shows the calculated band gap value. The pure PVA shows the band gap of 6.6 electron volt, whereas in the silver doped samples shows a less energy value, that is 5.42 electron volt. That is, we can conclude that the addition of silver doped sampling reduces the band gap to a lower region. This slide shows the FTR spectra of pure PVA and silver doped PVA. The FTR spectra shows the characteristic peaks at the OS stretching band at 3300 centimeter raised to -1, CH stretching vibrations at 2940, and C double bond or asymmetric stretching band at 1731, 1415 at CH to scissoring, 1251 and CO stretching band, and 832 correspond to CC stretching band. The silver doped PVA film shows an intensity increasing in the peak positions. We also conducted some dielectric studies using this pure PVA and silver doped PVA. The figure A shows the dielectric constant versus low frequency graph, and the B1 shows the dielectric loss versus low frequency graph. From the graph, it is clear that in the case of silver doped PVA, there is a reduction, there is an increase in dielectric constant. That is, pure PVA is a colorless polymer which shows a characteristic value of dielectric constant value, and the silver doped PVA shows a higher value of dielectric constant in low frequency region, and at the high frequency region, this dielectric constant value, constant value is reducing. This is explained in the case of conducting metal nanoparticles, and in the case of insulating metals PVA, the dielectric permittivity of the composite material increases as theoretically due to a large conductivity mismatch between these two materials. The PVA and Ag nanoparticle leads to a relaxation process, which can attribute an interfacial in polarization, which contribute this high value of dielectric constant. And we also observe that the dielectric loss decreases with the frequency, and in low frequency region, this decrease is more prominent. We also measured the dielectric loss tangent. It also noticed that the silver doped sample shows a less loss tangent value. We also calculated the complex electric modulus value M star and M double star from the above data. We found that the imaginary part of the dielectric modulus versus low frequency shows an absorption, shows a maximum peak, and as in the case of silver doped samples, this maximum value shifted to low frequency region. We also plotted the pole diagram. The nature of the relaxation is predicted by this pole diagram. This semicircular well depicts the samples are following the Debye model. We also calculated the AC conductivity, and it shows that silver doped samples shows a less conductivity value, or only a slight diminishing in the conductivity value in low frequency region, but in high frequency region, that is almost coinciding. The major conclusion of this work is the PVA and silver doped thin films were successfully deposited by simple solution cast method. The structural characterization of the produced sample were done using XRD analysis, which confirms the material's amorphous nature. The UV visible absorption spectra demonstrate that the indirect band gap decreases with the Ag plus ion doping. In FTR spectra of silver doped samples, the primary functional groups exhibits a greater signal intensity that demonstrate that the carbonyl group can function as an active electron donor when interacting with the Ag plus cation. At room temperature, the frequency dependency of the dielectric characteristics of pure and silver doped samples were studied. The fold diagram illustrates that the relaxation process in PVA film and the silver doped PVA films displays a semicircular plane that represents the debate model. Thank you. No.
Yeah, no.
Okay. Okay, Malini, you can.
Yeah. Anu, I would like to know, you said you have doped the sample with silver, right?
Yeah.
So how did you do that process?
Yeah, actually we are using the solution casting method. We prepare PVA solution and then silver nitrate, so 0.1 millimolar silver nitrate solution is prepared and stir these solutions and transfer to a petri dish and keep it in an hot oven for 48 hours at a temperature of 70 degrees.
So how could you know that it is a silver nanoparticle in that PVA? You have incorporated.
We can compare the pure and silver doped sample. It's the color itself we can identify the pure PVA is a colorless sample. That's a transparent one. The silver doped sample is in yellow color. In addition to we observe and in UV spectra we observe a additional characteristics peaks of 424 nanometer.
That is of silver nanoparticle.
Yeah, that is due to silver nanoparticles. Black one is PVA, only PVA. There is no peak in 424 nanometer. In the case of silver doped samples, we observe that is 424 nanometer.
It's only very small absorbance. Intensity is very, very small. Okay.
Yeah, that is why only doped only 0.5 weight percentage silver. Okay. This is only an initial study. We are trying to vary the weight percentage.
You have also said you have drawn call plot for both PVA and silver doped PVA, but your call plot is
this is for pure PVA. In a low frequency region, there is some noise. So that in the case of silver doped PVA, but we can find there is a decrease in value of M star in the case of silver doped.
Okay, and what about this curve is for? You have only one curve here.
This is for pure PVA.
And what about silver doped PVA? You have
that is in the case of that case. There is a in low frequency region. There is some noise due to that interpolarization. That is due to that Maxwell-Walker polarization, interfacial polarization in low frequency region. Okay, so
your conductivity value also shows that with silver doping your conductivity is decreased.
Yeah, conductivity is decreasing in low frequency region only.
Low frequency region means your conductivity value decreasing means towards the DC conductivity value you are getting a decreased value of conductivity.
Yeah.
Is it against the normal?
That due to that interfacial polarization. In low frequency region, there is an interfacial polarization. That may be that's why I do this electrical modulus studies. We can eliminate that value in this.
Okay, fine. Yeah, thank you. Ultimate.
Okay, Malini. I have only one question. What is the potential application of this study?
Yeah, the polymer combo. We can use this as a polymer composite in many applications in like this microelectronic devices application, also in charge storage capacity application, sensor application, because PVA is a flexible material. So we can use that in
Okay.
Hello.
Hello.
I have some doubt. If you use only silver nitrate, then what is the mechanism? Actually, the SPR peaks around 420 nanometer. I think it is Ag0 particles.
Yeah.
Okay. Then if you use only silver nitrate, it produce Ag plus.
No, silver nitrate and PBS is acts as a reducing agent in this case.
PV act as reducing agent in this
It's
process.
also. So it acts as a polymer matrix and it also acts as a reducing agent.
Okay.
Any more question?
Okay, fine. I think we can go for the next presentation.
Okay, ma'am. So the next participant is Hasina, ID number 073. The title is Non-enzymatic glucose oxidation of nickel oxide rich nickel or nickel oxide nanocomposite in alkaline media towards sensing application.
Ma'am, am I audible?
Yes.
Yes.
Good morning. Myself, Hasina Koikutti, doing a research under the supervision of Professor M. Junaid Bushri, Cochin University of Science and Technology. Here I am going to present my work entitled Non-enzymatic glucose oxidation of nickel oxide-rich nickel oxide nanocomposite in alkaline media towards sensing application. Plan of talk. Let us introduce nickel oxide and nickel. Nickel oxide is a transition metal oxide with a cubic crystal structure. It is a p-type semiconductor with a wide band gap, and exhibits antiferromagnetic ordering at room temperature. And it is well-known electrocatalyst for a wide variety of electrochemical reaction. Nickel is a transition metal. It exhibits ferromagnetic ordering at room temperature, and it is well known for its redox behavior in alkaline media. Nanocomposite. Nanocomposite is a multi-constituent material. It shows intrinsic properties of individual constituents and some additional properties due to the synergy between different constituents. We can tailor the properties of nanocomposite by tuning the properties of individual constituents. Let us introduce electrochemical sensors. Electrochemical sensors are one of the most versatile sensors used for simple, rapid, and economic detection of different analytes and used in wide range of fields such as clinical diagnosis, agriculture, and food technology. Here, in electrochemical sensors, receptors such as enzymes or antibodies immobilized on the electrode surface produce a response which is proportional to the concentration of the analytes absorbed on the modified electrode surface. Here we measure a current response which is proportional to the concentration of the analytes at a fixed voltage. This kind of electrochemical sensors are specifically known as amperometric sensors. The motivation behind our work is conventional glucose sensors are enzyme mediates glucose oxidation and produce a detectable current response. As we know, enzymes are affected by various physical conditions such as temperature, humidity, pH, etc. This in turn affected the sensitivity, selectivity, and stability of the glucose sensor. Moreover, nickel-nickel-oxide nanocomposite shows good redox property. It is naturally abundant. It is biocompatible and cost-effective. The objective of our work is the study of electrochemical glucose sensing property of nickel oxide-rich nickel-nickel oxide nanocomposite employing cyclic voltammetry and amperometry. These are the characterization tools we used in our present study. Here we synthesize the nickel oxide-rich nickel-nickel oxide nanocomposite by solution combustion technique. The XRD pattern shows the presence of both nickel oxide and nickel phases, and the nickel phase is dominating phase, showing the formation of nickel oxide-rich nickel-nickel oxide nanocomposite. To investigate the electrochemical activity and the glucose sensing ability of our composite, we perform cyclic voltammetric analysis. For this, we use a 3-electrode cell setup with AgCl as reference electrode, nickel oxide-rich nickel-nickel oxide nanocomposite modified glassy carbon electrode as working electrode, and platinum wire as counter electrode in 0.1 molar NaOH electrolyte. Here we perform series over a potential window of 0 to 0.8 volt at a scan rate of 20 millivolt per second. The CV of our electrocatalyst, that is nickel oxide-rich nickel oxide GC, shows a well-defined redox peaks showing the electrochemical activity of our composite. And in the presence of 1 millimolar glucose, our analyte CV shows an increase in peak current, showing the glucose sensing ability of our composite. Here we perform series of nickel oxide-rich nickel oxide GCE in 0.1 molar NaOH at different scan rate. The calibration plot of current with square root of scan rate shows a linear increase in both cathodic and anodic peak current with very high correlation coefficient, showing the electrochemical activity of our nickel oxide-rich nickel oxide GCE in 0.1 molar NaOH is diffusion controlled. To investigate about the sensing ability, sensing performance of our composite, we perform chronoamperometry analysis. This graph shows amperometer responses towards successive addition of 0.5 millimolar glucose. From the calibration plot of current with glucose concentration, the linear range of our sensor electrode is 1 millimolar to 11.5 millimolar, and sensitivity of our sensor is 16.66 microampere per millimolar per cm square, and the lower detection limit is 1.02 millimolar. Let us conclude. XRD pattern confirms the formation of nickel oxide-rich nickel oxide nanocomposite. CV measurements reveals the glucose sensing ability of nickel oxide-rich nickel oxide nanocomposite. CV measurements reveals the diffusion control electrochemical activity of nickel oxide-rich nickel oxide nanocomposite. Chronoamperometry reveals the glucose sensing ability of nickel oxide-rich nickel oxide nanocomposite over a wide linear range of 1 millimolar to 11.5 millimolar. The sensitivity of the sensor electrode is 16.66 microampere per millimolar per cm square, and lower detection limit is 1.02 millimolar. Reference, acknowledgements. Thank you. Hello.
Okay, Hasina, that was a good presentation. Let me ask some doubts.
Yes,
have you
ma'am.
checked the detection limit of this composite for glucose sensing? Can you hear me?
Yes, sir. Yes, detection
Have you
limit of
checked
sensing.
the
Yes,
detection limit?
it is not checked. It is calculated from the CV. From this calibration plot.
Okay. Okay. Again, how is the performance of this composite?
Actually, it is
compared to other sensors?
Actually, it is very low, but we can able to increase the performance using this as a base composite base.
Okay. Okay.
Mm.
Hasina, over to you, ma'am.
Yeah, ma'am.
Yeah, yes, Hasina.
Yeah.
That was a good presentation, and I need to know what is the advantage of your composite over other detection methods? What do you suggest? What do you suggest the advantage of your system?
Yeah, actually, this nickel oxide nanocomposite if we able to develop this is a transition metal or metal oxide based composite is very cheap and economic, and if we can able to develop it, we can able to develop it as a good sensor.
What are the other sensors being used nowadays?
Nowadays we use enzyme based glucose sensor.
Enzyme based.
Yeah.
Yeah, fine. Just a moment, Hasina. I would also like to know what is this chronoamperometry? What are you doing in that? Just show me that slide.
Yeah. Actually, yes. Yeah. In chronoamperometry analysis, we fix a fixed voltage, and then we measure current response against time.
At a fixed voltage, you are measuring the current.
Oh yeah.
It's a function of time.
Oh yeah.
Okay.
During this measurement, we add our analyte continuously to the cell system.
Okay. Okay. Thank you.
Okay.
Thank you.
Yeah, please.
The next participant is Anjali Jos, ID number 074. Title is Nanocrystalline Cerium Tungstate and its dysprosium doped forms with high NIR reflectance.
Good morning. Am I audible and my screen is visible?
Yes, yes.
Good morning. I am presenting the nanocrystalline cerium tungstate and its dysprosium doped forms with a high NIR reflectance. Cerium tungstate nanoparticles find catalytic and pigment applications, which possesses distorted chelate structure crystallized in a monoclinic crystal system with a distorted tetrahedral tungstate. It possesses both cerium-3+ and cerium-4+ oxidation states, which possess many oxygen vacancies in the structure. The motivation of the study is to study the optical spectroscopic properties and NIR reflectance of cerium tungstate and its dysprosium doped form to check the suitability to use this material as cool pigments in paints. Chemical precipitation method is used for the material synthesis, and it is followed by calcination at 600 degrees Celsius. The chemicals used are cerium nitrate hexahydrate and dysprosium nitrate hexahydrate as the cation sources and sodium tungstate as the anion sources. Here I have done 6 small percentage of dysprosium, and the samples are named as dy0 and dy6. The characterization studies used are X-ray diffraction, EDS spectroscopy, TEM, FTIR, and UV-Vis NIR reflectance spectroscopy. From the XRD pattern, we can say that only the cerium tungstate phase is C for both the doped and undoped samples. And it confirms with the C2-C phase group confirmed from the ICDD file number 980401920. And the crystalline sizes for the undoped sample is 20.52 nanometers, and for the doped samples, it is slightly decreased as 18.7 nanometers. The EDS analysis confirmed the presence of elements cerium, tungsten, and oxygen in the undoped samples, and additionally dysprosium in the doped sample. This is a transmission electron microscopic images. From the bright field image, it is clear that the particles are agglomerated, and the SID pattern confirms the polycrystalline nature of the sample. The similar observation is seen for the dysprosium doped samples. And here the FTIR spectroscopic patterns. The weak absorption bands are seen at 3,432 and 1,629 centimeter in width, which are the peaks due to adsorbed water molecules due to the symmetric stretching and the symmetric bending modes of hydroxyl groups. And the intense absorption bands at 942, 825, 732, and 686 centimeter inverse peaks are observed for undoped samples, and additionally 455 centimeter inverse peak is observed for dysprosium doped samples. All these absorption bands are due to the tetrahedral tungstate groups. The diffused reflectance spectroscopy, it is seen that we can see high reflectance, nearly about 84% and 80% for the undoped and doped samples. This high NIR reflectance enables these materials to use as cool pigments in paints. The corresponding absorption spectrum and the dot plot of the undoped samples is seen that it shows an absorption edge at the visible end at 500 nanometers, and it has strong absorption peaks in the ultraviolet regions about 350, 302, and 235 nanometers, corresponding to the absorptions of cerium. The absorption at 235 nanometers is only due to cerium 4+, which is the charge transition from oxygen 2- to cerium 4+. And the other transition 350 nanometers is due to cerium 3+. And the superposition of both cerium 3+ and cerium 4+ absorptions takes place from 300 to 350 nanometers. This strong UV absorption helps the material to use as UV filters in coatings and paints. This is the absorption spectrum of the dysprosium doped samples. The visible, the absorption edge starts at 510 nanometers, and the band gap is about 2.98 electron volt. As in the previous case, the cerium 3+ and the cerium 4+ absorption peaks are visible here. But additionally, we can say that some other absorption peaks are observed in the NIR region. This NIR region is enlarged, and we can say that for the dysprosium samples only there is 4F transitions taking place. This 4F transition, the schematic diagram is plotted here, and this additional peak seen here is the FF transition of cerium 3+ at 2,275 nanometers, and DD transitions of cerium 3+ at 1,945 nanometers. The dysprosium level transitions are taking place from 6s15/2 to the different levels which are obtained in the NIR region as tabulated in the table. Conclusion. XRD studies confirmed the crystalline monocline chelate structure of undoped and dysprosium doped samples with a slight variation in crystalline sizes. The characteristic vibrations of tetrahedral tungstates are confirmed from FTIR spectra. EDS analysis confirmed the presence of elements present in the sample. The optical absorption spectrum shows 5 absorption transition, that is intraconfigurational FF transition of dysprosium ions in the NIR region, and the intense hypersensitive transition at 1,296 nanometers. The high optical reflectance of more than 80% makes cerium tungstate and dysprosium doped cerium tungstate a potential material as cool pigments in paints. The materials show strong UV absorption properties, hence it can be used as UV filters while applied in coatings and paints. Hence, the strong UV absorption and high NIR reflectance makes cerium tungstate and dysprosium doped cerium tungstate a potential candidate to use as pigments in paints. Thank you.
Okay, Anjali. It's a good presentation. What method is used for this synthesis?
I used
of this?
okay, ma'am. I used a chemical precipitation method
Okay.
followed by calcination at the 600 degrees Celsius.
Is there any effect of the synthesis method on the properties?
Actually, from the SEM analysis, we have what spherical particles, and this method is very environment friendly and easy method.
Okay. Over to you, Malini.
Thank you, ma'am, and thank you, Anjali. It was a nice presentation. I just want to know whether your material is a direct band gap or indirect band gap material.
I have plotted the direct band gap at 3.06 electron volts, but it has both the direct and indirect band gap transitions.
But for dysprosium doped sample, your band gap is reduced.
A little reduced.
Okay. And you have also done ADS analysis of the samples. And is the proportion of the various elements are as expected?
Dysprosium amount is seen in the EDS spectra. It is not as expected as in the doping. The stoichiometry is not obtained as expected,
Okay.
but we have got
But still,
dysprosium peaks.
Yeah. Thank you, Anjali.
Thank you.
Thank you. The next two presenters are absent. So judges, please note, we are moving on to ID number 077, Bhagilakshmi K. Title, The Effect of Bottom Electrode Material on Resistance Switching of TiO2 based ReRAM.
Is the presentation is visible?
Yes, it's visible.
Let us start. I am Bhagilakshmi, MSc Physics student, Government Arts and Science College, Calicut. So, typically, electronics has been defined on three fundamental circuit elements, which are resistors, capacitors, and inductors. So, it was found that there is no element to connect magnetic flux and charge. So, in 1971, Leon Chua mathematically proposed a fourth fundamental circuit element, which is termed it as a memristor, that is memory plus resistor. So here we have investigated the effective bottom electrode on the resistance switching of these memory devices, and our device for the TiO2 thin film sandwiched between a top tungsten electrode and the bottom electrode that we are used to wear ITO coated glass and the gold substrate. So what is typically resistive switching? It is the reversible changes in the electrical resistance of two terminal device that occur upon external electrical bias in a non-volatile fashion. So what is a non-volatility? So let us consider the conventional semiconductor memories that we are using so far, like STAM, DRAM, and flash memories, in which flash memories are non-volatile. That means it can retain the data even if the power is turned off, but other two are volatile. When the speed is taken into account, the flash memories are slower compared to the other two. So a memory to be considered as a future memory or an emerging memory, it should combine all the best features of current memories. So several memories are proposed, like an emerging memory like ferroelectric RAM, magnetic RAM, and phase change RAM, resistive RAM. Among this, resistive RAM has the advantages of high integration density, fast switching speed, and non-volatility. So typical RRAM cell have a capacitor-like structure with a metal insulator metal structure. That means we cannot reproduce the switching properties with a metal configuration or any other configuration, because so that the insulator layer can be switched reversibly between two resistance states, that is the high resistance state and the low resistance state. So several materials can be used for this purpose, and we have chosen the TiO2 as a material because highly established synthesis routes and we can easily vary the oxidation state, and this is a low cost device. So we have chosen the salt gel spin coating method for the synthesis of thin films. So coming to the experimental part, we have prepared a 0.2 molar solution using titanium isopropoxide as a precursor and ethanol as a solvent. A drop of ethyl was used as a stabilizer, and this solution was stirred in a magnetic stirrer for 5 hours and aged for 2 days at room temperature. And this transparent and clear solution obtained was spin coated on substrate using a spin coater at a speed of 3000 rpm and acceleration of 500 rpm per second for 30 seconds. And each layer was annealed at 250 degrees Celsius. And after getting a desired thickness, the whole film was annealed at 250 degrees Celsius for 1 hour. And the electrical characterization was done by CZ-B2902 precision source measure unit and probe station setup. So coming to the result and discussion, for the structural characterization, we have taken the XRD. The figure shows the XRD patterns of film annealed at 250 and 400 degrees Celsius, and the 250 annealed sample was amorphous, and the 400 degree, the crystalline anesthetic peaks were started to appear after annealing at 400 degrees Celsius, and the average crystallite size was calculated using Scherrer equation and found to be around 20 nanometer. From the Raman spectra, we confirmed the annotated TiO2. So from optical characterization, we have taken the UV visible transmission spectra, and the figure shows the spectra of film annealed at 250 and 400 degrees Celsius. From the top plot, indirect band gap was calculated and found to be around 3.48 and 3.42 electron volt for the amorphous and crystalline samples. So coming to the main part of the work, that is the IV characteristics, which is a pinched hysteresis loop. This figure shows the IV characteristics of the TiO2 film deposited on ITO coated glass substrate. And as I mentioned earlier, there are two stable resistance states, that is high resistance state and a low resistance state. Usually, a electroforming process, which is a soft breakdown process, is required to bring the device to a low resistance state. So the transition from HRS to LRS is known as the set process, and the transition from LRS to HRS is known as the reset process. And depending upon the polarities of set and reset are same or not, the device can be further classified into unipolar or bipolar device. So this device 1 is typically a bipolar device, and there is no forming processes required for this device. To ensure it, we have fixed the reset voltage around 3 volt and see for different set voltages, and found that the hysteresis window opens only after when the set voltage exceeds some particular value around -4 volts. That means the device have a threshold voltage to switch on the memory properties. So due to that, the threshold voltage is absolutely equal to the forming voltage. The device does not require a forming process. So, and also we observe that there is a self-compliance properties, because usually a device require a current compliance to secure it from permanent breakdown. So here it shows self-compliance properties and have an RO to RO ratio around 10 at a 0.3 voltage, 0.1 volt. And this device, there are typically two types of switching, that is a homogeneous switching and filamentary switching. So this device, one shows a homogeneous switching. That means that can be attributed to the oxygen vacancy induced barrier modulation at the metal oxide interface. Typically, in a low temperature process of filling, there is an accumulation of oxygen vacancies at a TiO2 ITO interface. So, due to the oxidation of the tungsten electrode, there will be a small amount of oxygen vacancies at the top electrode. So, it will produce a Schottky barrier out there. Whenever a negative voltage is applied, due to that oxygen vacancies are positively charged species, it will attract it towards the top electrode, and it will reduce the Schottky barrier and set the devices to on state. Whenever a positive voltage is applied, the oxygen vacancy repel away from the top electrode, and the Schottky barrier increases and the device set to off state. So this shows the IV characteristics of device 2, that is the TiO2 film deposited on gold substrate, and we got a typical filamentary type switching, that is an abrupt change in the current was observed. So the forming cycle is also given, and we got a reduced operating voltage, and we have to set a current compliance around 10 milliampere, and the R of the R on ratio was found to be around 17 at the rate voltage of 0.1 volt. So it shows a filamentary type switching, that is require a forming process. So during the forming process, there will be a localized conducting channel will be formed to the active layer. That means the conducting channel is typically a McNally phase of TiO2. That means TIN or 2n-1, 2n-1 phase. That means an oxygen deficient phase. So whenever a negative voltage is applied in a device, then the magnetic field will grow towards the top electrode and the conducting channel will be formed and the electron can easily drift through the device and the device set to on state. Whenever a positive voltage applied, the conducting filament will be break and the device set to off state. So further modification of the device will be possible only after detecting the conduction mechanism and how it's related to the observed switching properties. So we have fitted our experimental data to various models proposed like ohmic, SCLC, pool Frenkel and Schottky emission mechanism. And here device 1, we have fitted our data to double logarithmic plot and we found that a linear relationship with a slope equal to 1 at the low field region. That implies that ohmic conduction mechanism is dominating in the low field region for both HRS and NRS. For the high field region, it's shown a non-linear behavior. So instead, we have fitted to log I versus V raised to half. We got a linear relationship implies that Schottky emission mechanism is dominating in the high field region. We confirm that the barrier modulation is responsible for the switching in the device 1. And for the device 2, we have fitted our data to double logarithmic plot and we got a slope at low field region, we got a slope at equal to 1 and high field region, we got a slope equal to 2. That means SCLC mechanism is dominating in the HRS and for the LRS, it is ohmic. So typically SCLC mechanism is attributed to the trapping and retrapping of electrons in the trap centers. So here the trap centers, oxygen vacancies will act as a trap centers. So this is a conventional mechanism. There are so many papers are published with this mechanism with the filamentary switching. So we have also checked the endurance, that is how the resistance changes according to the number of cycles, and we got a the device 2 was little bit unstable, but when memory properties, when compared to memory properties, device 2 have a better memory property than device 1 because there is a memory loss in the device 1 as the number of cycles are increasing. So we have also observed that the device 1, that is a TiO2 film deposited on ITO substrate, will get formed when the applied voltage is exceeded some particular value. That film get formed and we get a filamentary type switching, and the conduction mechanism is also steady and we got a SCLC type mechanism and ohmic mechanism here. And these two devices, I have mentioned a homogeneous switching device and a filamentary type switching device. These two devices have its own application. The homogeneous switching device can be used for the neuromorphic computing. That means we can recreate a human-like memory with these devices because in a human brain, the two neurons are connected by synapse. That means a metal insulator metal structure. So human brain also have a memory loss. The fabricated device 1 shows a memory loss. That means we can reproduce a human-like memory. That is exponential memory and exponential memory loss with these devices. And the device 2 can be used as a typical memory operation. That is the computer memory. That is LRS and HRS can be used as a logic 0 and logic 1. So the conclusions are low temperature solution process TiO2 based resistive memory have been investigated. The investigation of film by XRD, Raman and UV spectroscopic analysis revealed the highly transparent crystalline nature of films, and homogeneous switching exhibited by device 1 is attributed to oxygen vacancy induced barrier modulation at the metal oxide interface, and there exists a threshold voltage for switching, and the device shows forming free self-compliance properties. Ohmic and Schottky mechanism was dominated, and the filamentary switching in device 2 is due to the formation and rupture of conducting filaments in the TiO2 layer, and it shows the better memory properties with R to around ratio 17. And ohmic and SCLC mechanism were dominated, and the device 1 gets formed when the applied voltage exceeds some particular value, and it exhibited stable filamentary switching with reduced operating voltage and self-compliance properties. And these are the references, and thank you.
Okay, Bhagilakshmi, that's a good presentation. So you have studied the effect of bottom electrode material on the resistive switching of TiO2 based resistive. Okay, so what are the different bottom electrode material you have used in this study?
For the structural characterization, we have coated, for the XRD analysis, we have coated the TiO2 film on glass substrate. For the Raman, we have used the silicon substrate. For the UV visible transmission, we have used the quartz substrate. For the IV characteristics, since the bottom electrode should be conducting, so we have used the ITO and gold substrate here. And for the in further work, extended work, we have used the silver electrodes as well for the purpose.
Okay. And is there any effect of the thickness of this material on the resistive switching?
No.
Thickness of this bottom electrode, whether the thickness of the bottom electrode material affect the switching process?
Thickness of the bottom electrode doesn't affect, but we have started to study that thickness of the active layer, how it related to switching, because we have coated with the 3 layers, 5 layers, and 7 layers. The studies is going on how the thickness of the active layer will affect the switching. There is no dependence of bottom electrode thickness on the switching.
Okay. Okay, Bhagyalakshmi. Over to you, Madam.
Thank you, ma'am. And Bhagyalakshmi, that was a very good presentation. And I would just like to know what is the thickness of approximate thickness of various layers. If you have a single layer
for the single layer of TiO2, it will be around 30 nanometer. So we have coated around 3 or 4 layer, and it will be 100 nanometer.
Okay. And you were talking about a threshold voltage of 4 volt for device.
Yeah.
And what is that? Is it advantages or what is the typical values that you?
That is forming. Forming process will cause the deformation of active layer because it produces lot of defects in the material, and also it will destruct the electrode material as well. So researcher will looking forward for a device with a no forming device, and several papers will are published with the deposition of an active layer, that is a TI, a pure TI layer between the electrode and the active layer to remove the forming process. Because if the oxygen vacancies are large, concentration of oxygen vacancies are large, the forming voltage will be lower, and if whenever the switching voltage is equal to the forming voltage, the forming process will not be happen. So for that, oxygen vacancy concentration, to increase the oxygen vacancy concentration, several papers are published with the insertion of a TI layer in between. So it is an advantage that the devices are forming free because there is no destruction of the active layer.
Okay, and also regarding, just show me your endurance curve. You have shown a curve which shows endurance of the device.
Yeah.
Is that on the y-axis? It is a resistance.
Resistance.
Okay. Oh, with the different cycles of operation, how the resistance changes.
I'm not audible, ma'am.
It's the cycles of operation that you are doing. That
we will perform it for a 50 cycle. We can actually do it in the software. How many cycles we have to perform it? So we can use the 50 or 100 cycles. So during that cycle, this is the resistance. This is the high resistance state, and this is the resistance of low resistance state in the IV curve. So we can use the data from the spreadsheet and import to the origin, and we can plot it like this.
My question is whether device 1 and device 2 shows entirely different range of resistances. That is because of your active layer.
Yeah, that is because of the active, because the device 2 get formed. So there will be a conducting path in that device. So the resistance value will decrease because a lot of oxygen vacancies will be formed after the forming process. So the resistance value will be obviously lower in the device 2. But the ratio, the ratio will be higher for this than this.
Okay. Okay, fine. Thank you.
Thank you, ma'am. Can I stop my presentation?
Yes, Bhagyalakshmi.
Thank you. The next participant is Adira Maria Johnson, ID number 078. The title is Color Tunability Studies of Samarium Ions or Silver Nanoparticles Doped Titano-Silicate Glass Matrix. Adira, please.
Yes. Trying to share my screen. Can you see my screen?
No, we can't see. Adira, can you hear me?
Yeah, I can hear.
Should we share the screen now? Or will you
Yes.
share it?
Can you please share it?
Okay,
I
okay,
can't
we'll do it. We'll do it.
share it. Thank you. Yes. Can I start?
Yes, please.
Yes, please.
Thank you, ma'am. A very good morning to everyone. Myself, Adira Mary Johnson, a research scholar at CMS College, Kottayam, working under the supervision of Dr. Arun Kumar KV. And I'll be presenting the work on the title, Color Tunability Studies of Samarium Ions and Silver Nanoparticles, doped Titanosilicate Glass Matrix. An introduction followed by the synthesis method, and will be a discussion on the results and the conclusion. As an introduction, I would like to say that my primary aim is to synthesize a multi-component glass to use for multiple applications. The synthesis method uses non-hydrolytic sol-gel method, and we are focusing on incorporating rare earth as well as glass bonding nanoparticles in the colorimetric studies of the prepared samples will be followed. And the rare earth ions that we use is samarium ions. And why we are using the samarium ions? It is due to it is having a very narrow energy level structure, and samarium could be used for display and lighting devices as well as for optical applications. And silicates have emerged as a brilliant host that can serve as extensive luminescent material in lighting and display devices. And the emission wavelength of samarium ion is 568 nanometer, and it usually shows transitions from in the FF, usually rare shows transition in the FF range. And here, for the samarium, it usually emits reddish orange light owing to electronic transitions from 4G 5x2 to the 6H 5x2, 6H 7x2, 6H 9x2, and 6H 11x2. The plasmonic nanoparticles that I incorporated is silver, and silver is having it is an individual metallic particle with unique optical properties due to their size and shape, and it is having a somewhat low cost comparative to gold and platinum nanoparticles. And plasmonic nanoparticles are strong absorbers and scatters of light, and most importantly, they can be used in nanoscience and nanotechnology, and it supports the localized surface plasmon resonance, which gives account for the plasmonic nanoparticles. And the structural characterization. Can I have the next slide, please? The synthesis method employed was the non-hydrolytic sol-gel method. As we all know, sol-gel method is a method in which a sol is formed, which is a colloidal suspension of solid particles in a liquid medium and followed by the gelation. And it could be explained in 5 steps. That is a process of hydrolysis and partial condensation of the starting materials, either the precursors, and the gelation of the salt, then aging of the gel form, drying of the aged gel, and calcination at high temperature. And the advantages of the non-hydrolytic effective and easier method, and high purity of the samples, and homogeneity, and lower processing temperature. Either it could be made in the room temperature, and control of the surface and interfaces of the material, and control of the physical and chemical properties of the material. And what we have done is we have took the precursors as TIP for what we do is it is a titanosilicate glass matrix doped with samarium ions as well as silver nanoparticles, and the matrix precursor is TIP, which is the titanium isopropoxide, and TEOS for SiO2, which is tetraethyl orthosilicate. That the solvent employed is ethanol, and the catalyst used is nitric acid. And what we do is we take a combination of TEOS and ethanol, TIP and ethanol, and we stir it on a magnetic stirrer. And the rare earth ion samarium and also the silver nanoparticles, they are also mixed with ethanol, and all these are mixed together in the presence of nitric acid as the catalyst, and it will be stirred on a magnetic stirrer, and a liquid form is formed, and we'll be kept it for drying for 3 weeks, and after that we'll be getting a glass matrix, which is then formed silver nanoparticles. The annealing is taking place at 800 degrees Celsius. Can I have the next slide? Can I have the next slide? The structural characterization was done exploring the XRD, TEM, and FTIR. And the XRD analysis of the sample annealed at 750 degrees Celsius is given as that is the red colored peaks show the SiO2 and TiO2 sample docked with samarium ions alone, and the other one is SiO2, TiO2 with samarium and silver. The confirmation of the TiO2 nanophase as well as the silver nanoparticle is done in XRD. We are getting peaks at 25.32, 37.79, 75.3, etc. And the broad peak, which is centered at the 21 degree, at the 2 theta value of 21 degree, is the peak accounting for the amorphous nature of SiO2. And even though silica is non-crystalline, the broad peak is due to the presence of the short range order. And the characteristic peaks at 25.35 and 62.51 corresponds to the planes of titanium oxide, while the peaks at 37.9 planes of silver nanoparticles respectively. And the crystallite size of the sample was determined using the Debye-Scherrer formula, and it was found to be, the crystallite size was found to be 8 nanometer. Next slide, please. The TEM analysis was done to confirm the presence of the plasmonic nanoparticles of silver, and we got silver nanoparticles as a spherical structure in the TEM analysis, and the crystallite size was found to be 10 nanometer by plotting the histogram analysis. And the next analysis is the FTIR analysis. Can I have the next slide? FTIR analysis was done to confirm the matrix formation, and the glass matrix confirmation is done by the FTIR spectroscopic studies. There were peaks at 3,500 centimeter raised to -1 room temperature sample, which corresponds to the water which came from the ethanol. Our ethanol is only 99% purity, and there is some water content in it, and that is accounted in the FTIR. And the peak at 1,214 centimeter raised to 1. And the main peak, or the characteristic peak, is the peak at 953 centimeter raised to -1, which is the SiO-Ti bond, and the peak at 1,416 corresponds to the stretching vibration at TiO-Ti, and the peak at 860 to 990 centimeter is a typical range of SiO2 and TiO2 matrix. Can I have the next slide? The optical analysis is done by the UV visible spectroscopic analysis. It confirms the presence of the rare earth, which is the samarium, and UV visible analysis gives a confirmation of the presence of the rare earth elements, the samarium ion. Peaks are observed between 250 nanometer to 350 nanometer, and the peak around 330 nanometer is the one among the characteristic peak of the samarium. The peaks are in well agreement. The peaks which is observed for the samarium in the range of 260 to 400 nanometer. Usually, samarium is having peaks in the range of 260 to 400 nanometer. The peaks in absorption spectra responds to the transition from the ground state, that is 6H5 to different higher energy states. And the optical analysis is followed by the photoluminescence spectroscopy. The photoluminescence spectroscopy is a study of photogenerated electron. Samarium ions show strong reddish orange luminescence in the 550 to 670 nanometer range. The major peaks obtained are at 581 610, 662, 605, 619, and 668. And the spectra obtained to three prominent characteristic emission bands, that is 4G 5x2 to 6H 5x2, corresponding to 581 nanometer, 4G 5x2 to 6H 7x2, that is corresponding to 605 nanometer, and the 4G 5x2 to 6H 9x2, corresponding to 662 nanometer. There exists a variation in the intensity of the emission in the presence of plasmonic nanoparticles of silver, which could be a consequence of the difference in the emission spectra of the samples that is doped with silver is due to the interaction of silver nanoparticles with the samarium ions, and the plasmonic effect of silver is complemented with the presence of titanium. Can I have the next slide, please? The colorimetric analysis, it shows the color tunability in the presence of the plasmonic nanoparticles of silver. As you can see, the chromaticity coordinates are shifted from 0.6 to 0.38 to samarium plus silver, which is 0.6. Plasmonic nanoparticles, the psi coordinates can be tuned. Either the color tunability can be done using the plasmonic nanoparticles due to the energy transfer from the silver ions and the samarium ions. Moving to the conclusions, we have a titanosilicate glass matrix which is formed using the non-hydrolytic cost-effective Sol-Gel technique, and XRD analysis confirms the presence of the nanoparticles as well as the TiO2 nanophase, and the calculations done employing the Debye-Scherrer equation found the crystallite size as 8 nanometer, and FTIR studies confirms the presence of SiO-Ti stretching bond, and thereby the confirmation of the titanosilicate glass. Next slide, please. The further confirmation of plasmonic nanoparticle was done by the TEM analysis, which showed the crystallite size to be 8 nanometer, and the optical absorption studies of the titanosilicate glass topped with samarium ions gives the confirmation about the presence of samarium ion, and the peak at 330 nanometer is the characteristic peak of samarium, and the PL shows a strong reddish orange emission due to the presence of samarium, and color tunability was accounted, which is presented by using the colorimetric analysis.
Okay, Adira, that is a good presentation, and I just want to please show me your XRD, and you said there are peaks corresponding to silver around 37.
Yes,
With
yes.
and without silver sample, they are almost the same.
Ma'am, actually, TiO2 is also having a peak around 37.
Okay.
Both are having peaks around 37. That's why there is not much difference.
Okay, then what is the fingerprint of silver? You said it is visible from. Yeah.
Yeah, we have other, actually, silver is having a characteristic peak at 37 and 75.
Okay.
In the 75 range, there is a peak, which is the characteristic peak of silver.
Okay. And with and without silver, there is also that red colored pattern. Also, you have a slight small peak like.
One is around actually it was around 73, and for silver it is around 75, and titanium we have a peak around 25.35. That is a major peak of titanium.
Okay.
TiO2.
Yeah, and your PL result, and have you done it with and without silver?
We have done it with and without silver, but there was a problem when we were drawing the one bit without silver. So we are working on it actually.
Okay. No, because when you say color tunability with silver,
yeah, I have shown it in the colorimetric analysis. Both in the side plot, I have plotted it.
Okay.
Without silver.
Yeah, fine. So, thank you.
Thank you.
Okay, Adira, that was a good presentation. I would like to know, how do you choose the concentration of this samarium and silver for this
actually,
color?
Yeah. We have done it in a trial and error method. We have optimized the concentration as 3% of samarium and 3% of silver. We have done in 0.5% and up to 5%. We are facing the quenching process in which the effect is reversed.
Okay. Okay. Whether the size of the nanoparticle affect the color tunability? Did you check that?
No, we have not investigated on that.
Okay.
We are working on it actually. Further, we are doing the dielectric studies as well.
Okay. And the range of colors is as you shown in that diagram.
Yes.
That we cannot obtain from the study. Okay. Beyond that, what do you have to do? If you want to get other colors?
We can change the
Is there a
rarest ion as
possibility?
well. Yeah, we can change the rarest, and if we want a white color, we can incorporate along with samarium, we can incorporate europium and dysprosium.
Okay. Okay, Adira. Thank you.
Thank you. The next participant is Srija C, ID number 080. The title is The Effect of Zinc Doping on Absorption Coefficient and Conductivity of Tin Sulfide Thin Films Formed by Chemical Bath Deposition.
Okay, ma'am. Can I share my screen?
Yeah, you can share it.
Is it visible, ma'am?
Yes, Srija.
Okay.
Yes.
Okay, good morning. I'm Srija. I'm doing my research work under Dr. Anita Philip, Cochin College, Kochi. So today I'm discussing about my work, the effect of sudden doping on the optical properties on optical and conductivity of thin sulfide thin film formed by chemical bath deposition. So the main objective of my work is to synthesize and characterize a thin film of tin sulfide and sudden doped tin sulfide using CBD method, and to determine which of its property make it a good candidate for the absorber layer of solar cells. So first of all, what is a thin film solar cell? So a thin film solar cell structure is made up of a thin flexible arrangement of different layers. So light absorption and carrier generation occur in the absorber layer. So a solar cell absorber should be efficient in absorbing radiation energy, that is sunlight visible in the visible range. A certain thickness of semiconductor sustainably absorb the visible light, and always the absorber layer we use always P-type semiconductor material, and the window layer is N-type material. So our aim is to prepare an absorber layer material using tin sulfide. So why we use tin sulfide? It is abundant in nature, non-toxic, high absorption coefficient, insoluble in water. It has near optimal direct band gap of around 1.3 to 1.5 electron volt, high level of environmental and chemical stability, and it is brown in color, and it shows orthorhombic structure. So we use the methodology or the method of preparation is chemical bath deposition. So why means it is simple implementation, non-sophisticated equipment required, relatively low temperature. We need relatively low temperature for preparing tin sulfide thin film, and we can also have a large area deposition. So these are the synthesis method, and here cationic and anionic solution we use this stannous chloride and thioacetamide as tin and sulfur source. And here we prepare 1 molar solution of tin chloride and also 1 molar solution of thioacetamide. Using some buffer solution and complexing agent, we can prepare the chemical bath. And after preparing the chemical bath, a clean glass slide is dipped onto the solution for 60 degrees. The prepared film was dried in normal temperature. And then we add a zinc dopant like 0.1 gram, 0.2 gram, and 0.3 gram on the tin chloride solution, and the procedure is again repeated. So these are the characterization we done. First of all, the structural characterization. So for understanding the structure, we use XRD analysis. So these are the XRD pattern we got. And here the main orientation is around the plane 1-1. That means the prepared film have orthorhombic structure. And the crystalline size we measured using the Scherer formula, and the size of the particle is 11.2 nanometer, and these are the lattice parameter we measured. And for analyzing the chemical composition of the prepared film, we consider the IDAX spectrum. So this is the IDAX spectrum of pure SNS. So this is the chemical ratio 50.6 and 49.4. So we got a good chemical ratio of tin sulfide. And this is one of the film, that is 0.2 Zn SNS film IDAX spectrum. And here we can see the presence of Zn in the prepared film. And this is the atomic ratio, that is sulfur in the range of 47.04, Zn 3.51, and Sn 49.45. And this is the same image of the prepared film, and this gives the surface morphology of the film, and we can see a homogeneous surface morphology for the prepared thin film. This is for SNS, pure SNS, and this is 21 Zn SNS, and this is for 0.3 Zn SNS. And this is UV spectroscopy, that is optical characterization. So optical band gap energy of the synthesized particle were calculated for the absorption spectrum. Band gap energy can be obtained from the graph, and we consider the graph of h nu versus alpha h nu the whole square in the region of strong absorption. So extrapolation of the straight line portion of the curve to the zero absorption coefficient value gives the energy band gap. So this is the spectrum, absorbance, wavelength, the characteristics of the prepared thin film like SNS, 0.1 grams Zn SNS, 0.2 grams Zn SNS, and 0.3 grams Zn SNS. And we can see the maximum absorption is taking place in between 500 to 800 nanometer. And using this absorption spectrum, we calculate the absorption coefficient like alpha equal to 2.303 A divided by T, where A is the absorbance. And the value for 0.2 grams Zn SNS, absorption coefficient of the thin film 0.2 Zn SNS is around the 10⁴ centimeter inverse. And for SNS, the absorption coefficient is slightly less. And this is the top plot for calculating the band gap energy of thin film. So we got the band gap is ranging from 1.36 electron volt to 1.78 electron volt. So for pure SNS, the band gap is 1.36 electron volt, the direct band gap. And for 0.1 Zn SNS, the band gap is 1.41 electron volt. And for 0.2 Zn SNS, the band gap is 1.44 electron volt. And for 0.3 Zn SNS, the band gap is light high, that is 1.78 electron volt. Okay. So this is the conductivity measurement. We only done the type of conductivity measurement using hot probe method, and the analysis given that for SNS, 0.1 Zn SNS and 0.2 Zn SNS, the film show p-type conductivity, and as the concentration of Zn is increasing, the conductivity is slightly changing from p-type to n-type. So in our case, in the case of solar cell, the main component of thin film solar cell is the absorbable layer. So in thin film solar cell, the absorbing layer is the semiconducting material that absorb the highest number of photons and in response excite electrons into the conduction band. So here we can see in the absorption spectrum, the maximum absorption is taking place in between the visible region, that is 500 to 800 nanometer, and the conductivity also shows p-type conductivity. That means the prepared SNS thin film we prepared using CBD method is very successful, And the 111 crystal plane was the preferred orientation, and the structure is orthorhombic using XRD data. So the precise chemical makeup of the thin film is revealed by the EDAX spectrum, and we got a very good chemical composition. Also, the absorption spectrum is maximum absorption is in between 500 and 800 nanometer. That is, the film can absorb the maximum visible light. Also, the band gap is ranging. We can tune the band gap between 1.36 and 1.78 electron volt. And the material is p-type for low concentration of Zn. And as the concentration of Zn is increasing, the conductivity is slowly changing from P to N. And so these all characteristics match those to the material used as the absorber layer in solar cell. So these are our work, ma'am.
Okay, thank you, Srija.
Okay, ma'am.
Yeah, that was a good presentation, and I just want to know, have you maintained any particular substrate temperature, or what are the substrates that you have used?
Yeah, I tried from room temperature to maximum 90 degrees Celsius. But as temperature is increasing, here we are using chemical deposition method. So as temperature is increasing, the precipitation rate is increasing. So we always consider around 45 to 60 degrees Celsius.
As the optimum temperature?
Yeah, at the optimum temperature. After 60, the precipitation rate is increasing. That means the film surface is not homogeneous.
Okay, what is the approximate thickness of the film? Have you studied it?
Around 30 micrometer.
And you have a pinhole-free pure film.
What, ma'am?
You are getting pinhole-free film without any.
Yeah.
Kind of.
Yeah.
Okay. And and you have said you have prepared. What are the different concentration? What are the different open levels that you have used?
Ma'am.
You have used a zinc, right?
Yeah.
And you said sometimes you say it is 0.1 gram, 0.2 gram, 0.3 gram, and in your graph it is written as 0.1 molar, 0.2 molar.
Yeah, that is in only one graph. It is by mistake. It is
the correct one. Which is the correct one? You are using
gram,
molar.
Only
ratio?
gram. 0.1, 0.2, 0.3 gram.
Gram in how much? Or what is that weight? Is it in weight percentage, or I just want to know the proportion?
No, in 10 ml of water, 0.1 gram of zinc chloride we added.
Okay. Then just show me your SEM. I suppose both the SEMs are the same, or are they different?
Yeah, for 0.1, 0.2 zinc SNS, we got the same film, but for 0.3, it is like a granular structure.
Okay, and up to 0.2, you have p-type conductivity, and
yeah, I can show p-type conductivity.
Okay, so beyond that, you have n-type. Which is preferred, p-type or n-type for the absorber layer?
Absorber layer, it is p-type is preferred, but in solar cell, in my next aim is in solar cell, the window layer is considered as n-type material. So if I can prepare this SNS, pure SNS with the zinc doping, if I can prepare n-type material also, that is good, I think. I don't know.
Okay,
it is
that's okay. Okay, that's okay. Over to you, Sheena, ma'am.
Okay, Srija.
Hello, ma'am.
It was a good presentation. You have studied the films with the 3 concentrations of the zinc, isn't it?
Yeah.
Which one is the optimal doping concentration for achieving best coefficient, absorption coefficient?
For absorber layer, it is up to 0.2 because in 0.3, I got the absorption peak in the same level, but while measuring the conductivity, it is n-type. I just checked with the hot probe method, and I'm trying to measure the conductivity using hot probe. The work is going on.
Have you checked the thickness of the film?
Yeah, thickness for 0.2 Cetton means in that film we check the thickness that is about around 30 micrometer.
Okay, Srijan. That's fine.
Okay.
Thank you. The last participant is Jean Maria Matthews, ID number 081. The topic is wear and friction properties of PAEK ceramic nano composites reinforced with sol gel derived nano layer fillers.
Hello. Hello, am I audible?
Yes.
Okay. Is my screen is visible?
No.
Now it's visible, no?
No, it's not visible.
Then can you share my PPT?
Yeah, we'll share it.
Okay.
Yeah, now it's coming, I think.
Okay.
It's not visible, but it's showing that you're sharing the screen.
Hello.
Yeah, it's okay. You can share it. It's visible.
It's visible. Okay. Okay. Good morning to all. My name is Dr. Jean Maria Matthews. I'm working as assistant professor at Department of Physics, Newman College, Thodupuzha. The title of my presentation is Wear and Friction Properties of Peak Ceramic Nano Composite Reinforced with Sol Gel Derived Nano Layered Fillers. There are plenty of opportunities in different strategic field for oilless ultra-low friction lubricant that can control the noise as well as enhance the performance and life of the structural components. Development of such solid lubricant has been strongly taken up in metal matrix composites and alloys for more than decades rather than ceramics. The reason is that ceramics are brittle and not machinable. Moreover, the high density and high temperature processing are also limiting the development of solid lubricants based on ceramics. Actually, the lubricant is a substance that is introduced to reduce the friction between moving surface. Usually, we are using liquid lubricants. Liquid lubricants allows dramatically decrease the coefficient of friction. Today, in our daily life, we are dealing with various machines. Frictional loss is one of the important laws in machines. So while we are using liquid lubricants, it is impossible in certain applications in which ceramic parts operates under the condition of high temperature, vacuum, or corrosive environment. In such situation, continuous supply of solid lubricants to the ceramic surface may be provided by the ceramic material itself if it is a composite material with a ceramic matrix containing dispersed particle of the lubricant. But the low machinability of the ceramics prohibit such applications. So certain composite self-lubricating materials are designed. This slide shows some innovative lubricant composite, which is fabricated by incorporating certain ceramics in polymer matrix. Such hybrid composite designed out of suitable ceramic dispersion in polymer matrix can improve the wear resistance without affecting the toughness and machinability of the polymer. So here, this work introduced ceramic polymer composite self-lubricating material. The processing of nano-layered ceramic filler through sol-gel technique to impart lubrication effect in ceramic polymer hybrid nanocomposite having thermal stability, low friction and wear properties is discussed in this work. Here I have selected a polymer called PEEK, polyaryl ether ketone, as polymer matrix. Here this polymer possesses high temperature stability, low moisture absorption, density of 1.3 gram per cc, and almost high melting point of 370 degrees Celsius, and glass transition temperature 70 degrees Celsius, and high machinability. But its disadvantages are its hardness is very low, it poses high wear, and it shows swelling at high temperature. So in order to control or enhance these disadvantages, I have incorporated certain ceramic fillers into it. This is the characterization of pure PEEK polymer. And the particle size and some images are shown here. And for enhancing its disadvantages, I have incorporated alumina and lanthanum phosphate grains, which are synthesized through sol-gel route, and the sol-gel route for the synthesis of bomite salt and the lanthanum phosphate salt is shown here. These salts are dried, and I obtained alumina and lanthanum phosphate grain, which are incorporated into PEEK matrix. This is the same microstructure of alumina and lanthanum phosphate grains. This is the experimental part for the fabricating lanthanum phosphate alumina PEEK nanocomposites. This alumina and lanthanum phosphate grains separately dispersed in PEEK polymer matrix, and it's blended properly. After hot melting, ceramic polymer hybrid nanocomposites are obtained. This is subjected to thermal expansion, wear and friction properties. This is the same microstructure of PEEK alumina nanocomposites. This images are for different percentage of loading of alumina grains in polymer matrix. This shows for 10% loading and 20% loading, it shows proper blending between alumina grains and polymer matrix. After that, it shows some detachment of ceramic fillers from the polymer matrix due to overloading. The same for lanthanum phosphate grain in PEEK polymer. This is the variation of thermal expansion of PEEK alumina lanthanum phosphate nanocomposites. The expansion of PEEK polymer is controlled due to the incorporation of ceramic fillers. The hardness of the PEEK alumina lanthanum phosphate hybrid nanocomposites shown here. The hardness measurement is done using Climax Vickers hardness tester. The polished sample is subjected to a weight of 100 gram for time duration 15 minutes. Then it's observed that with the increase in the grain loading, the hardness of the composite is increased. And this is the variation of wear properties of polymer ceramic composites. It's observed that with the incorporation of lanthanum phosphates grains and alumina grains, the wear properties is reduced up to 30 volume percentage. Beyond that, the wear is increased due to the detachment of ceramic particle from the polymer matrix. This wear testing is done in a polishing machine. The sample is polished for 1 minute, and initial and final weights are measured. The weight loss is measured for each percentage of ceramic particle loading, and it's observed that up to 30%, the wear resistance of the polymer ceramic composite is enhanced due to the incorporation of these grains. In conclusion, the study brought out a range of wear resistant and thermomechanically stable polymer ceramic hybrid composite that can find applications for fabricating bearings, sleeves, and interface thin films. The appropriate loading limit of ceramic face was optimized as 30 volume percentage. The incorporation of alumina lanthanum phosphate to peak enhances the wear resistance and hardness of the composite compared to pure polymer. Thank you.
Thank you, Jean Maria. And I have few doubts. Like you were talking about the maximum loading, like it's around 30% or something, right?
Yes,
you are talking about the maximum
yes,
loading.
ma'am. Yes, ma'am.
Yeah, and is it because of something like the percolation threshold or something like that?
Yeah, yeah. After that, the detachment of particles observed, the grains, or due to the overloading. Up to 30%, we are getting low wear loss and hardness also.
So you are preparing the polymer and the composite.
Not polymer. I have
Yeah, you are taking the polymer
grains.
and you are preparing the grains and loading it the polymer with the grains, right?
Yes.
And you have a hybrid nanocomposite formed.
Yes, ma'am.
And you are making it in the form of sheets or what are you doing?
Actually, I made it in the form of pellets. Pellets for testing the wear test and hardness. We need pellets. So I fabricated in the form of pellets.
Okay. So when it comes to a device or comes to application level, what could be the form? What is the advantage of?
Actually, this is for machine parts.
Okay.
So we can design this peak polymer is highly machinable. We can by incorporating 30% of filler particle, we can retain its machinability. In any form, we can shape it.
You can modify the hardness. You can modify.
Yeah, wear resistance also.
Wear resistance. Okay. Okay. What about the stability?
Thermal stability.
Yeah.
Actually, it's a polymer, no? So up to 500 degrees Celsius, we can. It's stable. This composite is stable.
You have tried the curing of peak.
Yeah. Yeah.
Okay. Thank you, Sheena ma'am.
Okay, Jean, that was a good presentation. So what is the role of this nano-layered fillers in improving this wear and friction?
Actually, this lanthanum phosphate possesses layered structure. This layered structure render self-lubricating property to the polymer composites. Actually, for lubrication effect, we are using liquid lubricants like oils. These have some disadvantages. We can't use such lubricants in high temperature application or vacuum application, etc. But by incorporating these fillers, these ceramic fillers into the machine parts, that will act as a self-lubricating material. Then there is no need of liquid lubricants like oil and all.
Okay. Okay, Jean. That's all.
Thank you.
Thank you. So we have reached the end of the session. On behalf of STAM International Conference 2023 and Marathanesius College, Kodamagallam, I extend my heartfelt thanks to our evaluators, Professor Dr. Sheena Xavier, St. Xavier's College, Aluva, and Professor Dr. Malini K.A., Vimla College, Thrissur. I would also like to thank all the participants who have done their presentation.
Okay, thank you. Can we leave now?
Yes, ma'am.
Thank you.
Thank you, ma'am.
Okay, thank you, Malini.
Thank you, ma'am. Thank you, ma'am.
Okay, bye-bye.
The next session of online oral presentation will start at sharp 12:30 p.m. Thank you all.